Hello, my name is Don Jackson, and I'll be presenting the paper, A System for Measurement and Analysis of Aircraft Noise Impacts. This paper was authored by myself and my colleagues Tom Reinfleisch and Juan Alonso. The three of us together comprise the Metroplex Overflight Noise Analysis Project, or MONA for short. If you'd like to get in contact with me, I can be reached at dcj@aircraft-noise.org. I won't speak for my colleagues, but here are my motivations for this work. In the US, air traffic procedure changes resulting from the FAA's Next Gen program concentrated flight traffic into narrow paths. People under these concentrated routes experienced increased overflights, resulting in annoyance and complaints. I'll note that the areas affected are typically far away from the traditional DNL 65 contour. Many of those impacted are advocating for air traffic control procedure changes. One of those advocates is my wife. My perception is that these discussions, debates, and decisions might benefit from more factual data, including quantified impacts and visualizations. To that end, I began working to collect ADS-B and sound level data, and soon met and joined forces with my co-authors to start the MONA project. The goals of the MONA project are to provide objective data, reports, and analyses to stakeholders and policymakers to inform decision-making, using objective, factual measurements of San Francisco Bay Area regional aircraft traffic and the resulting ground noise impacts. We aim to leverage the power and accessibility of the web to provide our visualizations and analyses. In order to quantify and analyze the noise impact of aircraft overflights, we need to know where and when aircraft fly, what noise do aircraft overflights generate on the ground, flight and aircraft metadata, the details of aircraft traffic routes and procedures, and wind and weather conditions. Our current ground station for these measurements consists of a networked single board computer with an SSD. We use a power over Ethernet to provide both network and power. We include a GPS for timing and location, a standard ADS-B receiver. We support a sound level monitor that uses USB for both power and real-time data transfer. All of this is integrated into a weatherproof enclosure for outdoor deployments. It's important that it's remotely manageable and ideally that it's remotely power cyclable. We need to transfer and collect all the measurements from our sensors to our servers. Some of the challenges this presents are that the ground stations are capturing ADS-B messages and sound measurements every second of every day. Also, we subscribe to some real-time data feeds, for example, the FAA SWIM datasets. Some of the requirements that we have is that we'd like this to be highly available. We don't want to lose data when a server undergoes maintenance, reboots, or fails. For some applications, it's highly desirable to get access to the measurements as quickly as possible. In some earlier versions of our system, it could take hours or even a day to upload new data. A lesson I learned the hard way is that it's important to decouple the collection of real-time data streams from the subsequent stream processing. The solution we're using currently is Apache Kafka, which is a distributed event log. Kafka is a superset of most message queue broker functionality, provides built-in support for multi-server clustering. It supports real-time clients and subscribers, but the real-time nature of that is not a requirement. It's got integral support for stream processing and SQL-like queries on streams. It's open source, it has a large and vibrant ecosystem, and client libraries for many languages are readily available. ADS-B positions alone do not provide a complete description of the flight. Important missing metadata includes the airports of arrival and departure, assigned runways, air traffic control assigned routes and procedures, airframe and engine models, and who owns and operates the aircraft. Some of the sources we use to obtain this metadata include external services like FlightAware's Aero API, the FAA Flight Registry, OpenSky's Aircraft Metadata Database, the FAA's Coded Instrument Flight Procedures, and we are currently working to integrate the FAA SWIM data feeds. The real-time data streams are collected, processed, fused with available metadata, and ingested into a Postgres database that we've extended with PostGIS to support geospatial queries and processing, and Timescale DB, which extends Postgres support for very, very large time series tables. Our sound level measurements contain noise generated from all sources, but which of those peaks or events were caused by aircraft? In order to figure this out, we use a methodology that we call determined aircraft position location for aircraft noise extraction, or deplane for short. We determine the time and distance of aircraft closest approach to the sound monitor location. We use signal filtering and matching to isolate and identify the sound peaks. We match the sound peaks at aircraft TCAS, and we extract the noise metrics from these matched peaks. Other known implementations of this methodology are described by Harding and Ferrier, which is the basis of the ANEEM product, and Giladi. To give a quick example of this methodology, here is the raw output of one of our sound level monitors. Where are the planes in this time series? First, we filter the raw time series to smooth it out. Next, we compute the background noise level, and from there, establish a threshold. Next, we detect peaks above the established threshold. Finally, we matched these peaks to the time of closest approach of aircraft and extract the metrics from those peaks. So now we know where deplanes are in our measured sound levels. We'll never have enough sound level monitors to measure noise everywhere that we'd like to. Our aspirational goal is to use software to predict the noise generated by all aircraft flights throughout the entire San Francisco Bay Area at the desired resolution. The FAA's recognized noise and emissions prediction software is AEDT. It runs on Windows PCs, and its primary usage model is via a graphical user interface. How can we run thousands of flights per day over many years in an automated way? To automate AEDT, we leverage its use and reliance on a SQL Server database. We configure the SQL Server to allow access over the network. We taught ourselves how to create an AEDT study via copying and inserting into SQL tables. We developed a software library to enable programmatic study creation. We wrote code to process our ADS-B aircraft trajectories from the database into a valid AEDT flight track. We utilize AEDT's existing run study.exe utility to initiate execution of the study, again over the network. And then we extract the metric results from AEDT's database per aircraft, per receptor location. Finally, we combined all the above into what we call a study executor. In order to automate the running of lots of studies, we defined a study description format in either JSON or YAML. This includes the flight ID from our database and the IDs of every receptor location, which is generally where we have sound level monitors. We then enhanced our study executor to fetch a study description from a job queue, create and execute the study specified by the description, and finally to extract and enqueue the study results onto a results queue. We then package AEDT and the study executor into a virtual machine disk image for a commercial cloud provider. Now we can create as many executor virtual machines as desired using the cloud provider console or its API. We then wrote scripts that query our flight database, generate and enqueue study descriptions onto a job queue. Finally, we wrote a script that fetches study results from the queue and adjusts them back into our database. So now we can predict noise for every flight, every day, right? Conceptually, yes. But before we go to that effort and expense, the question is, how good is AEDT at predicting the noise for individual aircraft flying a specific, not an average trajectory, particularly at locations far away from an airport? The goal of our Ascent Project 53 is to do exactly that, compare AEDT noise predictions to measured noise. As I speak, we are actively using our system to compare the measured and predicted noise for thousands and thousands of flights. We look forward to reporting and publishing our results when they're complete. Our AEDT comparison approach is similar to that of Giladi, as he presented last year at the OpenSky Symposium. To give a few very brief examples of analyses enabled by our system, on the left is an analysis of DNL increases resulting from next-gen procedure changes. On the right is a comparison of average altitudes along two related flight procedures. The following three charts together tell an interesting story. Here we see the total flights per day by airport right before and after the COVID-19 lockdown. The dark blue line shows the number of complaints per day, which seems to track the number of flights closely. This dramatic decrease in aircraft traffic resulted in about a 3 dB decrease in measured DNL at 3 locations we monitor. This chart shows that the number of flights above 60 dB per day at the same locations also dropped by about half. These measurements and charts seem to support that the number above metric correlates better to annoyance than does DNL. We've developed a number of visualization tools and applications. Here we see a full day flight tracks. The user can choose any date. The data is fetched from our database. This app is built using deck.gl, which supports 3D WebGL accelerated visualizations. The app also supports sequencing through a range of dates, which is useful for viewing changes over time. The user can switch to viewing real-time flight tracks and can view interesting metadata by hovering or selecting on a flight. This application displays both real-time sound level measurements combined with marks showing aircraft times of closest approach. While working in my home office, I can hear approaching aircraft while viewing the measured sound levels and identified aircraft scroll by. The MONA ADS-B collection subsystem is similar to that of the OpenSky Network, but we operate at a much smaller scale, and we're currently focused only on our specific needs. Furthermore, OpenSky is also well open, and that is a future goal of MONA's. Key benefits our system provides are real-time access to ADS-B messages received by all the MONA receivers, and for historic data, ADS-B messages from all receivers are aggregated, deduplicated, segmented into flights, and stored in a local Postgres database, which enables high-performance access to flight and trajectory data. Trajectories can be represented as PostGIS 4D line strings, which facilitates powerful geotemporal queries. We also include specialized trajectory representations that are optimized for high-performance visualization, particularly animation. Here are some ideas I've had for potential MONA integrations with the OpenSky network. Could MONA feed our real-time ADS-B stream to OpenSky? Could MONA receive OpenSky real-time ADS-B streams from non-MONA receivers in order to increase coverage and to improve our resiliency and redundancy? Finally, to bring up instances of the MONA system in new geographic areas, it would be helpful to have batch access to OpenSky historic ADS-B messages. Our future work and directions include completing the AEDT prediction versus measurement comparison project, using our automated noise prediction system to understand noise impacts throughout the region. A system like ours is never done, and we're not even close. There's plenty of improvements we can make to data collection, access, and ingestion of non-MONA data, and the deployment of more sensors. Completing our SWIM integration, which should improve our access to and the quality of flight metadata. Improving ease of use and the ease of system installation and deployment. Improving scalability and providing logging, monitoring, and alerting of the MONA infrastructure. Finally, our goals are to increase openness, to provide self-serve end user access to our visualizations and analyses, open access to MONA data, and open sourcing key elements of the MONA software. Before finishing, I'd like to say a few last words. I am inspired by and admire the work of the OpenSky Network. I deeply regret that I'm unable to be there with you in Brussels for the symposium this year. And I hope that our paper and this presentation provides a basis for future discussions and explorations of potential integrations of the MONA system with the OpenSky network. Thank you.